Take it away.
Hey everyone, thank you guys for coming for week 2 of Winter Quarter. So today we're going to be going over deep neural networks. We're going to be reviewing a little bit of what we covered last week. Last week was intro to neural networks, and then we're going to go a little bit more in depth into the various concepts. Thank you. All right. So first of all, what are neural networks? So we're just going to be recapping what we went over last week and kind of understanding what are neural networks. So let's dumb it down a little bit. Let's start from the very basics. So what is a neural network? Well, you can think of a neural network as a neuron. I'm no bio major, but basically you can think of a neuron as you get a series of inputs. You get synapses firing, you get signals from the brain to various muscles and obviously the neurons in the brain. And the neuron does some calculations and it sends that input as an output to the next neuron or to the brain or to whatever nerve in your hand that you're using your brain to move. You can also think of the neuron or the neural network as a function machine. So this is a bit more programming based or mathematical, but you can think of a function machine. You have an input, you perform some calculation. You might not always know. It might be a black box. It might be some calculation that you don't know. And then you get an output from that function machine. So a neural network is very similar to these two examples that I just provided. You're just getting some input, you're looking for some pattern, performing some calculations, and trying to get an output or a prediction value from that input. All right, so this is what a neural network looks like, and we can just take a look and kind of analyze the different parts that we have here. So we have a bunch of circles, and each circle is usually called a node or a neuron. It's usually associated with some value. And we have the neural network, and as we go further into the network, we're getting deeper. So this assumes that there's some depth to the neural network. And you can add more columns or layers. So each column you can see is essentially called a layer. So at the leftmost side, we have an input layer. And the neuron or the neural network gets wider the more neurons you add vertically. The longer your column gets, the wider your neural network is. And so we have our input layer, and we have a series of hidden layers. So as we reviewed last week, hidden layers, we don't exactly know what calculations they have in very complex neural networks. But you can keep adding hidden layers to essentially find more complex data or create more complex patterns. And we get an output layer. We get some outputs after performing those calculations. So let's get a little bit deeper into the layers. So as I just reviewed, the input layer is the data that you're analyzing. So it might just be a classification. It might just be like, what is the correlation between the study time and sleep time? So it's some data that you're trying to evaluate, that you're trying to find a pattern for. And then we have the intermediate values. We have our hidden layers in the middle. And so the neural network essentially performs calculations. We're going to go a little bit more in depth into what calculations that a neural network performs, but they create the hidden layers. And so you kind of go further throughout the neural network with more and more hidden layers to finally reach a result value, some output value that we're looking at. It might be a prediction, classification. And so this output layer is basically our result value. It's the result that we get after we perform the calculations on the inputs. So as you can see, we have our input layer, and then we go further in to the hidden layer, and finally we get to our output layer. All right, so there's another important concept in neural networks, and those are called weights. So what are weights? Well, if you think about the diagram, it's just an arrow. It's an arrow connecting one neuron to another neuron. But an important aspect of weights is that each weight has a numerical value. And this numerical value essentially emphasizes the strength between the neurons. So the higher your weight value, the stronger your connection between neurons. And these weights can connect any neuron to any neuron. You can see a neural network is fully connected. Every neuron is connected to every neuron of the next layer. All right, so now we know all the components, but how does a neural network actually work? Well, there's two important things that we need to consider when we're actually working through the process of a neural network. One is forward propagation, and the other is back propagation, or backwards propagation. So forward propagation is the process of essentially going further and further through the neural network to essentially create an output. And back propagation is something that we tend to call training. I'm sure most of you guys have heard of like training a neural network before. We're going to go a little bit more in depth, but that's just an overview of these two processes. All right, so what is forward propagation? Or it's also known as forward pass, if you've ever heard of that. So essentially, we're passing input through the neural network, and we're using that to calculate some prediction. It's fairly simple if you think about it. You're passing some input. As you can see, we have the correlation of hours slept and correlation of hours studied. And those are just our inputs. And we're just going to put that through the neural network. The hidden layer is going to do its calculations. And we're going to get some graph or some prediction of this correlation between hours studying and hours sleeping. What is the prediction? How can we depict this in a graphical format? All right, so let's actually try to learn forward pass and see if we can actually figure out how a neural network works. So we have our input layer right here, and we have 3 neurons in our inputs. It's a pretty simple neural network, and we just have 3 values for now. We have 4, 3, and 2. So let's figure out how to actually calculate our output here. So, as you remember, a neural network has weights. So you see our first layer has 3 weights. Each neuron has an associated weight. We call it W1, W2, and W3. And they're all essentially feeding in to our first neuron here. So let's say these are our numbers. We have 0.2, 5, 1, and 0.5. So the formula essentially for calculating the value of our new neuron here is to multiply each value of each neuron in our input layer by its associated weight and adding that all up together. So can anyone calculate this for me? Anyone want to try calculating this? Huh? Is it 8? It's it's not 8. It's 5. That's right. You're right. But are we done? Does anyone know? Are we done? Is that it? Nope, right? We have something else we need to add. We need biases. So a bias is essentially a constant value added to the weighted sum at each neuron. And so each neuron has a bias. So it's not just multiplying each neuron by its associated weight. We also need to add the bias of that neuron. So let's assume our bias is 2. Then what is our new value of this hidden neuron? Addition. Anyone want to volunteer? What would be our new value? Yep, that's right. It's 7. So we just calculated the value of our first neuron in our first hidden layer. But let's calculate the next one. So let's say we have these values as our weight for our second neuron. Does anyone want to try calculating this? Well, you forgot to add the bias, but it's close. You're right. It's 4 plus 2, which would be 6. So that's the value of our second neuron. And so we could do the same thing for our third neuron. I won't bother you with the elementary math anymore. But yeah, you would multiply this all together, add the bias, and you would get 11. And now how do we calculate the output? How do we get from our hidden layer to our output layer? Well, it's literally the same thing. So we have each neuron and each associated weight, and we just multiply that all together, add each separate term, add our bias, and finally we'll get the value of 10. So that's our output value. And so I basically kind of summed it down into a formula. You think of the next neuron as each previous neuron multiplied by their corresponding weight plus the bias. You can also math it out. You can use symbols. So we have H1, N1 multiplied by W1. And so that's just the same formula, but a little mathematically. All right, so this is where we encounter a bit of a problem. So we have something called linearity or collapsing of hidden layers. Essentially, if you think about this formula, you can combine all the separate weights. Each weight is just a number. So you can combine all these numbers together into a bigger constant. And you essentially suppress this complicated function into a simple linear function. So this means that whatever data, whatever correlation that we have can only be represented in a linear format with a straight line. But that's not always good because sometimes we have complex data and we can't accurately represent that data with just a line. It leads to inaccurate predictions and sometimes, that's not what we want. Kevin, do you want a demo? Yeah.
So I've got a little demo here to kind of show what's happening because it can be a little confusing when we talk about layers collapsing into one layer. So I just want to go over again the importance of having multiple layers lets us model more complex functions. And so we want the math to keep those layers. But can anyone tell me what a constant is? Looking for one word. A number. Yeah. So a constant is a number, and we can represent this with something like A. Oh boy. Maybe we can represent it if we use a better marker. We can represent this with something like A, B, or C. Any of these are just numbers. So each of these are a constant. Now I want someone to tell me how many constants are in this equation. Can someone raise their hand? One. There's this constant here, but for the sake of this, we're going to say this is also a constant as well, a constant being multiplied by the x. What about this equation? How many constants? One, just one. That's correct. What about this equation? How many constants are here? That's a plus b. One constant. Very good. Why is that? Right. Each of these are just numbers. You can add them together and they will simply be another number, still one constant. What about a times b? How many constants are there? One. Right. So now I think we understand what a constant is, and I can go through and explain how these layers will tend to collapse. So for this example, we are going to have our inputs, which we're going to call x, and there's going to be 3 of them. We're going to have our first layer, which will have 2 nodes. We're going to call those y. And then we're going to have our final layer with only 1 node, which we'll call z. Does this make sense? 3 inputs, 2 hidden nodes, and then 1 output node. Any questions about that format? No. Okay, cool. So what this is going to look like is we're going to pretend all the bias is 0 because that just makes things a little more complicated. It still works, but for the sake of this demo, we're going to say, what's the equation for y1? No ideas? Ignoring bias, what's the equation for a node? Would it be a times x1 plus b? Wow, these all suck. That's even worse. If there are any markers up there, I'd love to borrow one. A times x1 plus b times x2 plus c times x3. Does that make sense? The first input times the first weight plus the second weight times the second input plus the third weight times the third input. Does that make sense? Okay, cool. What's the equation for the second node in the hidden layer? Y2. What's the equation for this? Someone shout it out. Thank you. Come on. Any ideas? It's okay to be wrong. In fact, it's good to be wrong. Yes. Close. Will they have the same weights? No. So can we use the same letter? No. So that being said, what do you think it'll be? Yes. Okay. What about the equation for Z? There's only one, so we don't need to subscript it. What's the equation for Z? Remember, you take the previous ones as inputs, you multiply them by weights, and you get your output. What's the equation for Z? It's okay to be wrong. In fact, I encourage you to be wrong. Being wrong is so much better than being silent. Y1 times Y2 plus bias. That's close. But remember, we're not multiplying the inputs together. We want to multiply the inputs by their own weights and then add them together. Anyone have any ideas? Almost, but is the output layer taking in the X's or is it taking in the Y's? This final layer, remember, each one feeds into the next. So, yes, it would be taking in the Y's. So we would have G times Y1 plus H times Y2. Does that make sense? It takes in the previous layers, multiplies them each by a weight. Now that we understand that, we're going to just do some simple substitution. I'm going to move this down here. So it's going to be plus H times Y2, literally just moving that. And then we're going to substitute in both Y's, the equations for both Y's here. Does that sound like a good plan? Does that sound like something we can do mathematically? This is a question, not rhetorical. Yes, cool, awesome. So I'm going to substitute in A times x1 plus B times x2 plus C times x3. And then here, D times x1 plus E times x2 plus F times x3. And now this is all addition. So we're going to rewrite it so that all of the x1s are next to the x1s, the x2s are next to the x2s, and the x3s are next to the x3s. Just rewriting so everything's next to each other. But first, we're going to multiply in this G into the first one and this H into the second one. Does that sound like a good idea? Just A times B plus C is equal to, or A times B plus C is equal to A times B plus A times C. That rule, the distributive property. Let's go ahead and do that. So this is going to be H, this is going to be H, this is going to be H. There we go, do the same thing here. This is going to be G, this is going to be G, this is going to be G. So we have GAX1 plus GBX2 plus GCX3 plus HDX1 plus HEX2 plus HFX3. And now what we're going to do is we're going to put all of the x1s next to each other, all of the x2s next to each other, kind of A plus B equals B plus A. You're just reordering around an addition. So now we have GAX1 plus HDX1 plus GBX2 plus HEX2 plus GCX3 plus HF. X3. Again, just reordering the additions. Now, do we remember the whole thing with adding constants? What we're going to do now is we're going to factor out the x1 and factor out the x2 and factor out the x3. So doing that factorization, remember, we just pull out everything else in parentheses, HD x1 plus GB plus HE x2 plus GC plus HF x3. I know my writing's getting a little messy, but now we're at the most important step. Do we agree that this is still X being fed into Y being fed into Z, as a perceptron or a neural network with 2 layers. This is still the same thing. We just did a bunch of math on it. But all the steps we did were valid. So what ends up happening is you see this here, this GA plus HD. Those are all constants being multiplied and added. This is going to turn into one constant. This is going to turn into one constant. And this is going to turn into one constant. They're all just constants being multiplied and added. And remember earlier, we said that that turns into one constant. So what's going to happen is we're going to have constant times x1 plus constant times x2 plus constant times x3. That's a single layer neural network. We just got rid of the layers. The layers collapsed. So what we do is in between each layer, we put a, we have this issue with linearity, and you'll see that in between we can put nonlinear functions. So with that being said, I'm going to pass the mic back to Rika, who will do the rest of the presentation.
Thank you so much for that demo, Kevin. That was great. So yeah, so after all the math, we kind of understand, okay, so this is collapsing of hidden layers. So this is a problem that we need to somehow correct in order to represent our data accurately. Could you unfreeze the... Yeah, okay. All right. So basically, let's kind of look at a depiction of like exactly what's the problem here. So which one do you guys think is a better representation of this data? Which line? This one, right? But the problem is when we collapse these hidden layers, when we basically smush the neural network down into a linear function, the way we depict our data is this way. So we have this less accurate representation of our data, and we want to somehow maximize it so that we can be as accurate with our predictions as possible. We can do this with activation functions. So basically, if you kind of simplify them, activation functions essentially prevent linearity. They prevent linear representation of the data, and they introduce nonlinearity. So nonlinearity is good because we get to represent the data in a more accurate way. And so we have like various different activation functions. I'm going to go a little bit more in depth into them, but here are just a couple of the most common activation functions that are usually used to kind of take in our linear function and introduce a nonlinearity component to kind of map our input values to our output values in a better way. All right, so let's kind of incorporate these activation functions into our neural network. So this diagram might look a little bit different from the neural network we saw earlier, but it's very similar. We still have our inputs. We multiply each neuron with its associated weight. We add the bias of our new neuron, but we're just going to add a little additional component here. We're just going to add our activation function. We're going to put this value, whatever value we get here, through an activation function. So it's no longer linear. We get a nonlinear representation of our new data. So this is just a diagram of the neural network and how we would now add activation functions into the process of a forward propagation. All right, so let's get into activations. So first we have sigmoid. Sigmoid is really nice for probability because all the values it outputs are between 0 and 1, which is amazing for probability. And because probability is very often used in classification, when you want to classify, which one is more likely to be a cat or a dog, probability is great, and sigmoid is great for classification. We also have 10H. It's very similar to sigmoid as it has values between -1 and 1. It's also fairly popularly used in classification, I would say. We also have ReLU. ReLU is really nice because if we look at the function here, everything below 0 is just cut off. It's every negative value is just a 0. And then everything from 0 and after that is a positive number. So the range of values would be from 0 to infinity. And as a result, it's really easy to compute, and it's very, very popular in a lot of regression or just in a lot of neural networks in general. Another function we have here, activation function we have here is leaky ReLU. Leaky ReLU is also really nice because sometimes when we have values or neurons that have values less than 0 or a negative value, we don't want to just discard it. We want to keep it active. So in those cases, when our range of values is from negative infinity to infinity, we can use leaky ReLU. So this is just a diagram on the popular activation functions, and kind of if you want to pick an activation function, how you would like look at it. Like for example, you can do it based on your network type. Maybe if it's a CNN, which we're going to go over next week, you might want to do a ReLU function. Or based on your problem. For example, if it's classification, you might want sigmoid. But if your problem is a regression problem, you might want to go linear activation. All right, so now that we've gone through the neural network, obviously we have some loss. So the predicted value as our output is it's going to be a little bit different from the actual value. So as you can see here, we have our diagram, a representation of the data, the line, and we have the actual data. And so if we do predicted minus the actual, that's how we calculate the difference or the loss. We realize that there is some difference between our predicted value and the actual value. And so now we want to figure out, okay, how do we train the neural network to kind of minimize this loss? Because obviously we want to be as accurate as possible. So what we can do is essentially calculate this loss, first of all, by using a loss function. Again, our goal is to minimize the loss. We want as less or as little loss as possible. So we have a couple popular loss functions. We've got mean squared error, which is popularly used in regression problems. So as you can see here, we kind of have the function for the mean squared error. We have a couple of different other loss functions as well. We have binary cross entropy, and because it's binary, it's more commonly used in classification, from what I believe. And there's also mean absolute error. So again, these loss functions are usually applied after you propagate through the neural network, and you use it to calculate the loss. All right, so now that we have the loss, how do we actually fix it? How do we minimize it? How do we fix our neural network to get as high accuracy as possible? Well, we're going to have to move backwards. This is where we go back into back propagation. We need to go backwards through the neural network and kind of update the weights in order to create new outputs that are a little bit closer to the actual value than our predicted value earlier. We want to optimize the neural network. This is updating the weights is basically another word for just optimizing our neural network to increase accuracy. And so again, this is where we go into back propagation, or a backwards pass. As you can see here, there's a little diagram of essentially how we would go back propagate through the neural network. All right, so now it's time to move backwards. And so back propagation essentially aims to minimize the loss function. We want to, if we think about it, our loss function tells us, okay, we have this much loss at this point, at this x and at this y, and we want to reach the lowest point possible. We want to minimize that value as much as possible. So we're minimizing the loss function by updating the weights in the neural network. And how do we do that? Well, gradient descent. So this is where we get into a little bit of calculus. A gradient is essentially a simple way to explain a gradient could be slope. So if you think about the gradient of a linear function, it would just be rise over run. It's just slope. But in more complicated functions, this would be calculus. We would use this, we would calculate derivatives in order to essentially find the slope of our function. And we essentially want to look for the absolute minimum. So again, this is a calculus term. An absolute minimum is basically the lowest point of the function. We want to find where the loss is the least in the loss function, and we want to kind of reach that point. All right. So again, gradient descent is the standard method. There are other methods to kind of minimize the loss, but usually gradient descent is the most straightforward and the best way to do it. Essentially, yeah. So what we use is the derivative, again, the gradient, to identify how to modify the weights. So how do we kind of shift the weights to kind of minimize the loss? So as you can see here, we have, this is a 2D depiction, but we have our weight values here. And as you see, as the weight values reach a certain point, our loss is at the lowest point. So we want to try to find those values. We want to find that value of the weight. We have a couple vocabulary terms here. We have epochs. So epochs is the number of trading iterations. We want to see how many times do we need to back propagate? How many times do we need to forward propagate in order to reach that point of the lowest of the loss function? And we also have the learning rate. Learning rate is essentially a scaling factor. It's just like how much do we shift the weights in order to how much do we update the weights in order to now see, okay, have we gotten closer to the absolute minima? Have we got further away from the absolute minima? All right, so if you look at this function here, this is a simpler 1D depiction rather than the 2D depiction. So we have our weights on the x-axis and we have the loss on the y-axis. So can anyone tell me exactly where is the absolute minima of this function? Or just approximately, what would be the weight value in which we reach the absolute minima? Yep, around where the weight is 3, and maybe the loss function is around it's about point something. So we want this blue dot here. This is probably our current loss, and we want to kind of move that dot down to where our weight is 3. But obviously we won't know that, so we would need gradient descent to find, okay, what value of the weight do we need to change to in order to reach that point. Again, so this is just a review of some of the vocabulary I just went over. So gradient is a partial derivative. If you've taken calculus, or even if you haven't, you will hopefully learn that. It's essentially calculating the slope of the loss function with respect to the weight. And the learning rate, again, is just the scaling factor. It's just how much do we need to update the weights by to find that point. Kind of a coding or coding terms. Basically, what we would do is take our old weight and, okay, well, first we'd have to take a gradient. Okay, so this is how much we want, this is the slope, and we multiply by how much we want to change by. And then we subtract it from the weight because obviously we're changing the weight by how much our learning rate and our gradient is. And then we update the new weight with that value. And so that's how we would keep updating the weights in every iteration to get closer and closer. This is just a GIF of essentially how you'd reach that kind of gradient descent. How do you reach that absolute minimum point? All right, so this is where we hit the problem of the vanishing gradient. So essentially, the gradient or the derivative decreases exponentially. And so when we use the sigmoid function, there's a point where you realize that the gradient doesn't change. It barely changes. It changes at a very minimal rate that's almost not noticeable. And so, or after 2 layers. So if you add more and more hidden layers, it hits a point where the change is basically unnoticeable. And so that's when you realize, how do we fix this? How do we change this so that we can actually see the gradient descent? We can fix where the gradient and have it actually change. Well, this is where we have ReLU. So the ReLU is good because you get a gradient of 1 when input is greater than 0. So which means that we eventually get a gradient of either 0 or 1. So we do actually get some value change. We fix the problem of the vanishing gradient. All right, so these are just a couple other things that we could use, optimizers that we could use other than gradient descent. As far as I know, Atom is very popular. You can easily find the absolute minima with Atom. So a lot of people tend to use Atom when creating a neural network. But these are just a couple other ones as well. All right, so we're just going to quickly recap everything we kind of went over. First, we went over forward propagation. Just always remember that you multiply each neuron by its associated weight. Then you add the bias to calculate the value of the next neuron. Then we went over activation functions. We're introducing nonlinearity. We're trying to fix the problem of collapsing the hidden layers. And then finally, we have back propagation. We're using the gradient descent and we're using loss functions to calculate, essentially, to minimize loss and reach as high accuracy as possible. And yeah, so we're trying to update the weights and the biases to reach that absolute minima. All right, so.
Hello, everyone. This is kind of a separate thing. We're proud to announce the return this quarter of our Sky's No Limit workshops and competition. So this is an AI workshop for beginners. So even if you have no previous experience in AI or making neural networks, even if you went to this lecture, so you maybe already got kind of a introduction to neural networks, but even if you, didn't understand what you said, these workshops are the perfect place to kind of dive more deep into how do you actually create these neural networks and make them in code, make them actually work and do stuff that you want them to do. We have the workshops every Wednesday. We have 2 back-to-back workshops. So basically a workshop from 1 to 2 p.m. and from 2 to 3 p.m. And it doesn't matter what workshop you come to. Usually we have the first workshop as a catch-up. So even if you miss a workshop, you can just come to the catch-up workshop and we'll catch you up on everything that you need to know to make your own neural network. Additionally, if you do create a neural network through these workshops, you can submit it to the competition. And there's $550 in prizes for submitting your neural network to this competition. So I would strongly encourage you to apply. You have a very strong chance of winning, even if it's your first time making a neural network. And it's also a great thing to put on your resume. It's really fun. I'd really strongly recommend it for anyone. That's Wednesdays 1 to 2 and 2 to 3 p.m. Are there any questions about the workshops? Yeah, okay. Go on by. We haven't had one this week yet. It's starting next week. Are we announcing the theme right now? Okay. Can we do a drum roll, please? I'm going to announce the theme for this quarter's competition. Cat out of the bag. So think about, yeah, we don't have a slide for it, sorry. But the theme is cat out of the bag. So you can think about something neural network to do with cats, to do with bags, to do with letting a secret come out. I don't know, something like that. That'll give you a head start to think of ideas. And that first week, next Wednesday, we'll be talking about how do you think of a good machine learning idea? How do you find a data set for your idea? How do you create your idea into a real model?
All right. Thank you, Anthony, for presenting Sky's No Limit. I highly encourage you guys join. It's a really fun competition. It'll be really fun. Does anyone have any questions about anything about that we covered today about deep neural networks? All right, cool. So we have a quick collab that you guys can just open on your computer. Here's the link. Just make sure to make a copy and don't edit the actual thing. And I'll be opening this up here as well. Yes. I can show it right here as well. So you can just click File and click Save a Copy and Drive right here. And that'll just create a copy of the collab. Oh, yeah. Yeah. Kevin's going to write the link there just because I'm going to switch tabs. We also have a link to the slides here from the collab if you guys ever want to reference the slides. But I'm just going to be going through this collab real quick. So we have cover type data set that we have here. And so we're importing various different Python libraries, pandas, matplotlib, numpy, tensorflow. These are very popular machine learning libraries in Python. Okay, yeah, all right. And so if you run this thing here, we're just going to be cloning the GitHub. Well, the GitHub has access to the dataset, so we're just cloning that right now. And we're converting the CSV file into a pandas data frame. So why are we converting the CSV file to the pandas data frame? Pandas is great for data cleaning or data processing. And so we want to convert it to a data frame to process it. So we're just going to be doing that. I'm just going to run this. If it works.
Sky.
Yeah. And obviously we can display the data set. We can see our data. We can see the elevation, the aspect, the slope. This is basically different forest covers. So we have different trees that are involved, and we can see each class or each tree and the value that's associated with each cover type. So we didn't really go over data processing today, but did I misrun? Here. This one. It should be fine. All right. And so what we're doing now is we're going to split our data into a training and testing. So it's important to split your data into training and testing because you want to make sure that there's a portion of your data set that you use to train the neural network. But then you also want to test the data set or the neural network on data to actually see the accuracy. So now we're just going to be building our model. So this is essentially how you add layers. So as you can see, you're adding different layers with different activation functions. So you see the functions that we kind of went over today: sigmoid, tanh, relu. And you can modify this a little bit. You can try switching it out to see if different activation functions represent the data in different ways. Because when you print it out, you can see the output shape. But this is exactly where you can play around here. So we have our loss function and our optimizer here. So we went over various optimizers, remember, like gradient descent, SGD, atom. And so we can modify our optimizer and the learning rate. So we can change update, we can increase and decrease the rate at which we kind of reach the absolute minima. And you can also change the loss function. We're looking at mean squared error, but you guys can try cross entropy or mean absolute error and see if something increases the accuracy more than other values. I'll fix this in a second. And you can also plot the data. So we can plot the loss function or we can plot the accuracy over in a graph. And yeah, so maybe take a few minutes, try to play around with it, and I will figure this out.
Metrics. Does it work without it? Yeah. Just yeah, that whole thing.
Yeah, all right. Yeah, so we will be publishing the collab and the slides on in our Drive and on Discord, so at our website. So be sure to check those out. Thank you guys. Let me switch that back here. Thank you guys for coming, and please keep in touch, join our Discord, join our Linktree. We have a feedback form here, so if you guys could take a moment to fill that out, that would be great. And we'll see you guys next week for CNNs. Thank you guys. And feel free to stay back if you guys have any questions.